Hello everyone, welcome to Computer Science 411, Digital Integrated Circuit. My name is Chongxu. I will be your teaching assistant this semester. Today, I'm going to talk about the course background. First, I will let you know what is this course about and what will we learn in this course. Then I will introduce you a very important term in digital integrated circuit, which is a fundamental element to build a large integrated circuit module. Today, the digital integrated circuits are becoming more and more important. You can almost find it everywhere, in your desktop, your laptop, your iPhone, iPad, or even your car. So where is this electronic device? There will be integrated circuits. So please think about what do you expect from your electronic device, say your laptop. I guess the first thing is you want a computer to be fast. So you want to watch your movie smoothly. You want to play your video game smoothly. And second, you probably don't want a computer to be too hot because you can never touch a laptop that's 85 Celsius degree. Third, but actually that's the most important one, you want a computer to be cheap and cheaper. So you can spend just little time, little money to buy a great thing. Last but not least, you want your computer to be reliable. I think almost everyone hates when you're just about to finish your homework but the computer crashes. So this course is all about how we can analyze, model, and improve the performance, power, cost, and the reliability of the integrated circuits. First, the course will teach you how to model circuits because a computer processor can have billions of transistors sitting in the processor. So it's not practical to look at the transistors individually and design them individually. So we need some level of abstraction. That's the model. So the course will teach you how we can model the transistors and the circuit modules so we can only focus on the high level abstraction. Second, the course will teach you to use a software to design your circuit. So you will be learning a language called HSpice. So you'll be writing in that language to describe the circuit behavior you're going to design. And also, you'll learn how to use the tool to generate the circuit diagram and the netlist after you write the circuit in the HSpice language. So after you design your circuit, the course will teach you how to measure your circuit you design. So how fast is your circuit? How much power does your circuit consume? And is your circuit reliable or not? So those are the issues a circuit designer should be concerned about. In summary, the course will teach you how to design a faster, cooler, cheaper, and more reliable circuit. So now let's move to the introduction of a transistor. So the first question is, what is a transistor? A transistor is nothing but an electronic switch. So what is a switch? This is a switch. So in a switch, you can open, you can close it, or you can turn on, you can turn off. So a transistor is a kind of switch. You can control the switch electronically. And how does a transistor look like? It looks like this. A transistor is basically a three-terminal device: a terminal source, terminal drain, and a terminal gate. So when the transistor is not working, the gate is connected to a zero voltage or grounded. In that case, the transistor is off. That means when you apply a voltage on the drain, the current cannot pass through the transistor, and we define the state as zero. But since it's switched, it should be able to be turned on. So how do we turn on the transistor? we apply a positive voltage here on the gate. And in that case, the switch is turned on. That means if you apply a voltage on the drain, the current will be able to pass through the transistor, connecting the drain with the source. And we define this state as state 1. So why does this happen? So let me explain using the energy band theory, which is very similar to the water flow. Okay, so when the transistor is off, its energy band looks like this from source, gate, to drain. Think of electrons as water, so when there is a high barrier here, sort of like a mountain there, the water cannot flow through the mountain to the drain, which means the electron can't pass through the barrier to the drain. But when you apply a voltage on the gate, the mountain is removed. The barrier goes like this one. And now the water had a chance to flush through the mountain to the drain. That means now the electrons can hop through the barrier from source to the drain. There are two types of transistors. The first one is called NMOS. It's just like the one I just showed you. You turn the transistor on by applying a positive voltage on the gate. And the symbol for this transistor is like this. And there is an opposite transistor called the PMOS, which also has three terminals, looks very similar, but if you want to turn on the transistor, you need to apply a negative voltage on the gate. So, and the symbol for the PMOS is also opposite. So this transistor can be used together to build the CMOS logic, the complementary metal oxide on silicon logic. Okay, we have explained what does a transistor look like and how does it work. So what can we use a transistor to build a circuit module? I will be giving you a very simple example. We will just be using two transistors, a pair of opposite transistors connected together like this. This is a four-terminal module. The top node is always connected to a positive voltage, say positive 1 volt, and the bottom node is always connected to ground, 0 volts. And this terminal is an input. This terminal is the output. We call this module an inverter. An inverter inverts input information to its inversion. Let's see how this inverter works. Okay. Because these two transistors work in opposite directions. So when you apply a positive voltage here, this lower transistor is turned on and the upper transistor is turned off. Then the output is connected to the ground. Then we have output of 0 volts. In the other hand, when you apply a 0 volt on the input, the lower transistor is turned off and the upper transistor is turned on. Then the output is connected to the 1 volt. Now you have an output of 1 volt. You can see output is actually the opposite of input. That's the fundamental element in circuit design. You have the function that you can invert something. Based on that logic, you can build more and more complex logic. And finally, you have your computer processor. So where do we build transistors? We build the transistor on a silicon wafer. So today, the silicon wafer is like this large, and the silicon wafer is from sand. So that's the reason why the computer processor can be cheap. But even the silicon wafer is this large, individual transistor can be very, very small. So in today's Intel processor, the feature size of the transistor is about 20 nanometers. So how small is that? So think of a single piece of hair. Even a single piece of hair is 1,000 times feature size of a transistor. So how many transistors can you have in a processor? Billions of them. So in your laptop, there can be 3 billion transistors, and that's almost the half the population of the world. So the course will first teach you how do we model the transistors. Once we have the model transistor, the course will let you know how we can use the model to build the very simple logic like the inverter, the NAND gate, the NOR gate, the XOR gate. And after you learn how you can build a simple logic, you can use that logic to build different circuit modules which do different things. For example, some circuit can perform the calculation, and some circuit can can be used as memory, which stores the information, and some circuit can be used as interconnect, which connects the calculation with the memory. Then we will learn the different design considerations for different circuit modules. For example, for the calculation circuit module, the number one metric is the performance because you want the speed of the calculation. You want your addition, your multiplication, your division to be done as soon as possible. But for the memory circuit module, the number one metric you care is its reliability because you never want to lose data in the memory. For the interconnected circuit module, maybe what you care about is the power. You don't want to spend too much power just in the interconnection, so that makes different considerations for different circuit modules. And the course will teach you how to optimize them separately. That's pretty much for today's introduction. So if you still have any questions regarding the course background, you can find me in the office hours Wednesday 3 p.m. in the room 354 in the IST building. Thank you all.